For 24.46, we have a parallel plate capacitor, and they tell us its capacitance to start with. It is 12.5 picofarads. Okay. And they tell us space between it's filled with air, so pretty much we're going to call that's going to mean that there's pretty much we can use epsilon naught. It's like having a vacuum. Okay, plate is circular, that's nice. Okay, the capacitance is going, this is going to do battery, and there's a charge placed on the plates. Okay, and then we put a slab of dielectric while it's connected to the battery. That's an important part. Okay, and it's still connected to the plates, so we're going to put a dielectric between them. So we're going to put it between while it's connected. Okay, that's okay. We know that now, and the charge increases. Okay. Then they ask us what's the dielectric constant K of the dielectric. Well, let's talk about that first. Well, we know that we can relate the capacitance of a unfilled capacitor to a filled capacitor by saying that C equals kappa, the dielectric constant, C naught. Okay. If that's true, and we know that if we use Q equals CV, C is equal to Q over V. The charge on the capacitor with the dielectric over the voltage of the dielectric filled capacitor equals kappa times the charge on the unfilled capacitor divided by the voltage on the unfilled capacitor. Well, the battery is the same. It's going to have the battery on both of them, right? So these two are actually equal. Okay, so we can actually divide them out. They're going to be the same thing. So, and we actually know both these values, so we can use the values that are given to us in the problem. Afterwards, it's 45, and I'm going to convert picocoulombs equals kappa times 25 picocoulombs. Okay, and I'm just going to divide those two. 45 divided by 25 is going to give me a kappa of 1.8. Okay, and that's going to be my value for the dielectric constant. Okay. That's 8. Okay. B asks me, what is the potential difference between the plates before and after the dielectric is inserted? Well, part of me thinks, well, I think this is a more obvious question than they ask, because they said that the battery is connected the whole time. So that means that the voltage can't change. The voltage has to stay constant. And I can figure out what that is because I know what the charge is initially was. So if I use Q over C, I can use the initial charge, 25 times 10 to the negative 12, because that's picofarads. Actually, I'm not going to do that. Divided by 12, and that's farad. No, that's coulombs. 12.5 times 10 to the negative 12 farads. I didn't even need to really write that, did I? Because you can see the answer is just 2 volts. Okay, and that's what it is before, and that's what it is after as well. Again, the same battery is connected, but one question is, well, now there's more charge on it, so why would it be the same? Okay, and that actually turns out to be kind of an interesting question. Okay. Let's say we have this, these are our plates, right? Beforehand, and again, I'm not going to draw all the charges, I'm just going to draw 2. Sorry, that's a minus, and that's a minus, okay. So we start like that, right? Well, that's going to have 1 voltage, and if I added more charges along here, which is what it says I do, you know, almost twice as many. Oh, I'm doing that. Okay, twice as many, right? So I should have twice as much voltage. But remember what my inserting my dielectric actually does. Let me put the dielectric inside here. That the dielectric is going to polarize slightly. So what's going to happen is we're going to get like a little bit of negative charge here, and a little bit of negative charge here, and a little bit of positive charge is going to induce here, and a little bit of positive charge is going to induce along here. It's not all going to become positive. It's not going to equal out, because again we have molecules locked in, or molecules and atoms locked in place. But we're going to have just enough redistribution inside this inductor that we're going to have a change that happens along there. So that's going to lead us to the exact same thing. That's going to lead us to have the exact same electric field going across. We have a net charge on this, on the left edge of positive 2, and a net charge on the right edge of that picture of negative 2, which is the same as we had before we put the inductor in. So we're going to end up with the same voltage both times, 2 volts. Part C asks about finding the electric field at a point midway between the plates before and after the dielectric is inserted. Well, it really doesn't matter what point we talk about inside the field, or inside the plate. The field is going to be constant between them. And again, you just use, I'm just going to use that voltage equals the electric field times the distance between the plates, and it's going to be constant. So I'm going to take the voltage, which we found was 2 volts. Okay. And we'd love to know the distance between them in order to find out what that electric field is. Okay. Well, we can find the distance between them pretty easily if I remember right, because we know all the other stuff about it. We go back to our definition of a capacitor to figure out where that distance is. So we can say C equals epsilon naught A over D. And they give us everything we pretty much need to know. Well, I'm going to rearrange this. So it's D equals epsilon naught A over C. And they tell us we know this is 8.85 times 10 to the negative 12th. This is going to be the area of it. They tell us the radius is 3 centimeters. We actually need that now. They're circular. So it's going to be pi 0.03 meters squared divided by the original capacitance, which is going to be 12.5 times 10 to the negative 12th. Okay. So we can divide all that stuff out. That gives you an answer of 0.002 meters. Now we can plug that in up here. 2 volts divided by 0.002 meters, and that's going to be 1,000 newtons per coulombs. Okay. And for the exact same reason that I gave before, it's not going to matter before or after the dielectric is inserted. We're going to have the exact same electric field. The voltage isn't going to the voltage across the plates isn't going to change, and the distance isn't going to change. So we're going to end up with the exact same electric field across the two.